Okay, so then now that it's 3 o'clock, we're going to get started. I want to thank everyone for joining us this afternoon. We're really happy to have these webinars. As I said, I'm Melissa. I'm with the National Ocean Sciences Bowl National Office. Each year, we like to have these webinars specifically for our NOSB coaches, but also for any interested educator, someone who wants to learn more about ocean science in general. These webinars are really to help prepare the coaches and their teams for the upcoming year of competition. But again, please feel free to share these with any of your educator friends, even if they don't have NOSB teams. We want them to be as useful as possible for the education community. Each year, the NOSB chooses a theme for the competition year, and this year we're focusing on our ocean shaping weather. Okay, sounds like a few people can't hear. Let's see. I'm just going to let everyone know. If you can't hear, potentially try calling in by phone. Although it looks like, now you can. Okay, maybe I'll just try to speak up louder. Maybe you just couldn't hear me if I was too far from my phone. As I was mentioning, our theme this year is our ocean shaping weather. We try to choose a theme that is, topically important for, the current year, but also that it fits in with our finals host location. And this year we're going to be hosting our finals in Boulder, Colorado, with our regional bowl, the Trout Bowl. And so obviously focusing on how the ocean affects everyone, including all of those who live in the center of the United States. Obviously it's going to shape your weather and your climate, so it's an important topic. This webinar schedule, this is the first webinar we have as part of this series. We hope to have 2 to 3 more in the month of December, so please make sure that you visit our website, or if you follow us on social media, we'll be posting about them on Facebook and Twitter as well. The way these webinars work is I have you all on mute just so that we're not interrupting the speaker in a few minutes, no dogs or phones barking in the background. But the presentation is going to be up to an hour, and then you'll have 30 minutes for question and answer. Good thing is most of you seem to know how to use the chat box. That's where I want you to enter your questions. So feel free to enter them throughout the webinar, throughout the presentation. But I'm going to save all your questions until the very end, and then we'll ask them sort of within that last 30 minutes of the webinar. So, okay. Also, I would like to note that you can always email us at nosb@oceanleadership.org. I'd love to hear what you think of the webinars. Both, this year we're using Zoom, which is new for us. So if you have any feedback on the use of Zoom as the platform, or if you just have any feedback on the webinar in general, we'd like to be able to provide that both to the presenter and just have it for our own purposes, definitely letting funders know how much this webinar helps you. And we will be posting these recordings of these webinars on our Facebook and our YouTube page. So obviously, as this webinar is geared towards coaches, we do want you to share it with your NOSB students. So definitely share it with them so they can watch it at a later date as they prepare for the competition. So today, I'd like to present Dr. Elizabeth Maroon. She is a postdoctoral fellow at CERES at the University of Colorado Boulder, and she researches climate variability and coupled ocean atmosphere modeling. So obviously fits very well into our theme for this year. And she has a presentation today on how does the Atlantic Meridional overturning circulation influence the amount of global warming. So I'm going to turn it over to her. And again, remember to type your questions into the chat box. Okay, Elizabeth, if you want to get started, the floor is all yours.
Sure, great. If you can't hear me, let Melissa know, and hopefully we'll figure out if there's any issues from my end. It's really nice to be able to give a webinar for you all today. I had a lot of friends in college who were involved with the National Ocean Science Bowl, and I'm from St. Louis originally, and not much of an ocean there, and this was not something I had in high school, but in retrospect, this would have been really fun. So I'm really happy to be able to help out a bit here and share some of the fun science that I like to research. So what I'm going to be talking about today is about the Atlantic Multidecadal overturning circulation, which is a key part of the thermohaline circulation in the ocean, and how it is related to the amount of global warming. So in general, when we think about ocean circulation, we kind of divide it up into these two parts, a wind-driven part and a buoyancy-forced part. So what I've got up here is a little schematic of the wind-driven part. So you can see that there's a bunch of gyres, there's currents. So here I've overlaid a couple of little, just the labels for some of these wind-driven currents. So the North Atlantic subtropical gyre, the Atlantic subpolar gyre, their counterparts in the Pacific. And these are driven by the winds. So you have winds blowing over them. You can do the math and come up with how the curl of the winds forces the gyres. And that's explains a lot of the closer to the surface ocean circulation. The second part of the circulation is the buoyancy-forced circulation, so also called the thermohaline circulation, or you may have heard the global conveyor belt, or abyssal circulation, or meridional overturning circulation. There's a bunch of different terms that get ascribed to this. And the idea, it kind of is that you can split all of the ocean circulation up into these two parts, one that's driven by the winds, the other that's driven by density differences. So when water gets dense, it sinks. Turns out, especially in the last 10 years of research, that this division into wind-driven and buoyancy-forced circulation doesn't necessarily work all the time. For instance, here's this a nice schematic of the thermohaline circulation. You'll see so the red is the surface flow of the thermohaline circulation. You'll notice that here's the Gulf Stream turns into North Atlantic current. That part of the overturning circulation is also part of the North Atlantic subtropical gyre. So how do you divide? Well, is this much due to the wind-driven part and this much is due to the buoyancy-forced part? And how do they interact? And there's been a lot of research in the last 10 years especially that says that this division between wind-driven and buoyancy-driven kind of works to first order, but there's a lot of places where it doesn't necessarily hold together. Like the Gulf Stream is one of these areas. In the Atlantic subpolar gyre, which is an important place for sinking in the ocean, a thermohaline process. These two things, the wind-driven subpolar gyre and the thermohaline sinking, are also very coupled. So to first order, you can say the ocean is wind-driven circulation and buoyancy circulation, but it's not that simple. So back to the thermohaline circulation. So thermohaline just sort of implies that you have temperature and salt, so thermo and haline, parts that are driving the whole circulation. So if we have sort of in schematic form, we have surface flow red on top. Green is the deep flow, so like 2,000 meters ish down, and bottom flow is the blue. You can see that you have sinking in 4 key locations, and then you see water that travels down at mid-depth through the Atlantic, and it gets swirled around the Antarctic circumpolar gyre. You have upwelling in different parts in the Southern Ocean, and so you get mixing a lot in the Antarctic and the Southern Ocean. You see that there's also upwelling in the Pacific. This is a key part for how we mix ocean water back polewards. The surface branch, you can see that there's a lot of surface water that gets ejected into the Pacific through the Indonesian through flow into Indonesia, around South Africa through the Agulhas Current, and that's one way that you can get water back circulating to the North Atlantic where it sinks again. So right here I have a nice animation from NASA where they sort of put together what the flow looks like in the thermohaline part of the ocean circulation, so the meridional overturning circulation. This is ignoring all the bits that come from the wind-driven part. So they start in the Atlantic. You can see these white arrows are the water flow on top. On the bottom, you can see that this is not the bottom, but this is like mid-depth, so 2,000 meters-ish. You have sinking in the Labrador Sea, and up here kind of more near the Iceland and Erminger basins. One thing they do not have in this graphic is that you also get sinking further north of Iceland in the Nordic Seas, but you have to get over that still, and they're not representing that process. You have to get the dense water over here, which also contributes to the North Atlantic deep water, which is what's being flowed along with these blue arrows. You can see the bottom of the ocean is pretty rough, which is important for mixing in the ocean, getting water upwell back up. Now we're scanning back out. There's the Gulf Stream, the deep western boundary current. You can see that the thermohaline circulation, we have water escaping from the Indian around South Africa. And that comes back poured in the Atlantic. There's the Antarctic Circumpolar Current. The Antarctic Circumpolar Current is a geostrophic current. And no need to worry about what exactly that means if you don't feel like learning geostrophy today, but it means that it's mostly wind driven, and it's also circumpolar around there, and it's goes through all of the depth of the ocean. It's not just at the surface, it's at the mid-levels too. So that's kind of a brief animation of all of the important parts of the thermohaline circulation. You can also see, I guess it doesn't go into specifics much, but you can see the Indonesian through flow. And so those are the main parts. I'm going to be focusing mostly on Atlantic processes rather than Antarctic or Pacific, because that's just where my research has ended up taking me. So I focus mostly in the North Atlantic, and part of that is because there's two key locations for deep water production there. The Labrador Sea produces more intermediate deep North Atlantic deep water, and the really deep stuff, not really deep, somewhat deep, is in the Nordic Sea. So you get slightly deeper North Atlantic deep water. The densest water in the ocean is formed in the Antarctic. So this is where the formation of Antarctic bottom water occurs, in the Ross Sea and the Weddell Sea. This is the densest water. It goes straight to the bottom. So it's what's represented by the blue lines at the very bottom. Something interesting you'll notice is that there is no sinking in the North Pacific. There's sinking in the North Atlantic, and the Labrador Sea is at the same latitude line as regions where you have open water in the North Pacific. So that's kind of an interesting topic. Why is there no sinking to deep depths, so like 2,000 meters in the Pacific? There is North Pacific intermediate water, which is formed near the Sea of Okhotsk and off the Kamchatka Peninsula. But this only gets down to maybe 1,000 meters, 900 meters, 1,000 meters. It's not deep, and it doesn't get very far from its source. So that's kind of an interesting difference between the Atlantic and the North Pacific. And the reason why there's more deep water production in the Atlantic is because the Pacific is fresher. So on the left, we have sea surface salinity. And you see that at the same latitudes, the water is fresher, and so therefore less dense than its counterparts in the Labrador Sea and across the Atlantic. It's at about the same temperature as water in the Labrador Sea. So you could say that it's probably not a temperature effect, it's a salinity effect. But something interesting that occurs with this is that this sea surface salinity being higher in the Atlantic and lower in the Pacific goes along with the fact that you have an overturning circulation, that has a Gulf Stream and has all of the northward flow at the surface in the Atlantic. So you could imagine that when you have higher salinity in the Atlantic and you have transport of that water poleward, you're taking more. The overturning circulation is taking this really salty water into the Atlantic. So the reason why it's salty up in the high latitude North Atlantic is because you have an overturning circulation, which is bringing that salt. So you get into a kind of circular reasoning there. The reason why it's sinking is because you have the circulation, which brings the salt, which drives the sinking. So you can't necessarily say that the Atlantic is saltier, and that's why you have the overturning circulation. You could imagine that if you were able to drive that, bring that salt poleward in the Pacific, maybe there'd be an overturning circulation there as well. So the fact that it's salty is an explanation for why there's sinking in the North Atlantic, but not the North Pacific, but it's not a full explanation. And there's a bunch of theories for why we have deep water production in the Atlantic and not the Pacific. And this is still an open area of research. There's been some idealized work showing that it's the geography of the basins that's important, that when you have a narrow basin, that is the basin that is going to be the one where you get sinking, versus a wide basin will be the one that does not have sinking. An idea that goes along with that is that it's the atmosphere, that you have freshwater transport from the Atlantic to the Pacific across Panama. So when you take when you have water evaporated out of the ocean, it gets into the atmosphere. The atmosphere has easterly trade winds in the tropics. The atmosphere blows that from the Atlantic to the Pacific and then rains out in the Pacific. And so because you have extra rain in the Pacific, you get fresher water. And you can't have an equivalent amount of fresh water make it from the Indian Ocean into the Atlantic. There have been a couple of studies in both models and observations that show that you transport more moisture out of the Atlantic basin in the tropics than you do into it. So that's probably one of the reasons why they're sinking in the Atlantic. It's possibly an atmospheric. It's part of being an ocean-atmosphere coupled system. But there's a few other ideas too. One is that you have this source of Mediterranean salt. So here the Mediterranean has a really high evaporation, so the water can get very salty. And when that water spills over into the Atlantic, it's a high source of salt, which could precondition the Atlantic basin to have more sinking. So that extra source of salt in the Atlantic is important, and you don't have an equivalent source of salt from any inland sea in the Pacific. Another important difference between the two basins is what's called Agulhas leakage, which brings salty water from the Indian Ocean into the Atlantic. So remember before we saw that there's a gyre in the Indian Ocean. The retroflexion, so the turning back of that gyre, occurs right at about the same latitude where South Africa is. And so because of where it's located, the gyre turning back doesn't occur all the way. So it occurs, but it loses some of the water around South Africa in the Agulhas current. And you get these Agulhas rings, which are really high salinity eddies that bring lots of salt from the Indian Ocean into the Atlantic. You don't have the same thing happening around South America. So this could be another source of salt into the Atlantic basin that preconditions it to have deep sinking. And then a theory that's kind of near and dear to my heart, because it's something I spent a lot of time in my dissertation thinking about, is that the configuration of mountain ranges on land is also important for influencing the ocean. There was an interesting study in 1983 by Bruce Warren. He said that the reason why there's sinking in the North Atlantic is because the Gulf Stream has a tilt, a southwest-northeast tilt. And the equivalent current in the Pacific Basin, the Kuroshio, does not have that tilt. It's a lot more just zonal. And he said, well, because it has that tilt, it makes it much easier to bring salt from the subtropics where you have high evaporation into the higher latitudes. And he says, well, why is there this tilt to the currents? And the reason why is because of the atmospheric circulation. So to first order, remember wind-driven circulations, the separation of the gyres is set by where you have your zero wind stress curl line. So just where the wind, when you take a look at how rotational it is or not, where that zero line is. And that zero line is set partially by the presence of the Rocky Mountains. So when you put the Rocky Mountains into a climate model, you see that it gives a wave in the atmosphere at the surface. So you have air that comes down across the continent and then back up. And that helps drive some of that difference between the Gulf Stream and the Kuroshio. So there's been some model studies which have taken out the Rocky Mountains and some that have taken out all of the mountains. And they find different results in whether you get sinking in the North Pacific when you take out mountains or not. So I think that's still an open area of research, is what is the impact of mountain ranges on ocean circulation. So I'm going to be mostly talking from this point forward about the Atlantic Meridional Overturning Circulation, or AMOC, because it's one of the most important parts of the thermohaline circulation when we care about climate impacts. So this is a recent schematic from a review paper on the AMOC, and sort of shows a slice from southern hemisphere Antarctica to the North Pole, which way the water is flowing and what the main water masses are. And then this figure also shows the age of the water through oxygen. So these you see in the top of the surface here is the surface flow. So you can see this is part of the Benguela Current across the, or at least if you were looking at this horizontally, that's where you'd see these currents being manifested. Then up here, this rest of the surface flow is part of the Gulf Stream and the North Atlantic Current. You have sinking both at about 60 north. So this is, again, Labrador and Erminger basins where you get the sinking. You also have overflow across the Greenland, Iceland, Scotland ridge. So up here is where you have sinking in the North Atlantic, sorry, not the North Atlantic, the Nordic seas. And then that water has to get over the Greenland, Iceland, Scotland ridge, which is an effective barrier for keeping it out. Because the water in the Nordic seas is denser, that flows underneath. So it's more, this is the slightly deeper part of the North Atlantic deep water, and the Labrador Sea part's a bit higher up. Together, these all transport southward, and then some of it is upwelled into, upwelled due to Ekman transport in the Southern Ocean. So the winds in the southern hemisphere near the surface, winds drive a mass transport to the left. So because winds are westerly at about 60 south, so you could imagine the winds coming toward us in this figure, you get mass transport to the left of that. So if it's coming towards us, left is northward in this case. And that's partly why you get upwelling there in the Southern Ocean. Which brings up another interesting point, that this division between wind-driven and thermohaline is not exactly clean, that the upwelling part of the meridional overturning circulation is partly due to winds. And so how is the overturning circulation wind-driven or thermohaline? And probably some of both. You also have deep water production in the Antarctic. Remember, I mentioned that this is occurring in the Ross and the Weddell Seas. This is some of the densest water. It sinks all the way to the bottom. Antarctic bottom waters, AABW is the usual abbreviation. And then the color on this plot is oxygen. So you can measure, a measure of the age of the water is how much oxygen is available in that water. The water that has been in contact with the atmosphere very recently is water that has a lot of oxygen in it. And the longer it's been away from the surface, the more respiration uses up all of that oxygen through processes of decay. And so the oldest water is the water that's been down there the longest, so this orange stuff has very little oxygen left because of respiration. Where you can see the more recent waters, so Antarctic bottom water here is more recently been near the surface. So in the large-scale climate, the reason most we care about the AMOC is because it transports heat northward in the entire Atlantic basin. So this plot on the left is the total heat transport in the Earth system. I tend to think about things, a very broad picture first, and then zoom in on the important part. So what we have here, as you can see, this is in petawatts. Petawatts is 10 to the 15th power. And so the red arrows indicate which way heat is being transported. So in the northern hemisphere, red arrow indicates in the ocean, the atmosphere, and total, you have heat being transported poleward, northward in this case, and then southward, energy is being transported from the tropics to the high latitudes in both basins. The reason why you have to have this heat transport is because the Earth is heated unevenly by the sun. It's round, so you get more heat absorbed in the tropics, and you have heat released back to space in the high latitudes. And nature does not like it when there's a disequilibrium. Nature wants everything to have about the same amount of energy, and it tries to make that so. And so somehow the atmosphere and ocean have to transport energy from places where there's lots of it to places where there's little of it. And since the heating is mostly done at the surface in the tropics, you transport heat from the tropics poleward. The ocean has a particularly large role of that in the subtropics, especially at the equator and the 40 degrees north. This is accomplished by mostly the wind-driven parts of the circulation, the gyres. So the Gulf Stream is an important part of this circulation. Once you get further poleward, it's more the subpolar gyre that starts to take over with this heat transport, and the subpolar gyre is also linked with the overturning circulation. You'll see that most of the heat transport in the mid-latitudes, so where we live, is done by the atmosphere. And in the latitudes where we live, the atmosphere is transporting the heat through storm systems. So anytime you listen to the weather at night and they talk about cold fronts and warm fronts and storms and there's a low here, that's what's transporting the heat. That's what, in our latitudes, that's what's responsible. In the tropics, it's something called a Hadley circulation that's responsible by the atmosphere for moving the heat poleward. So that's kind of the large schematic of why we care about the AMOC, because an important part of it is involved in the ocean heat transport. If we divide now this curve up into the part done in each basin, so the Atlantic, Pacific, and Indian, the Atlantic stands out in comparison to the Pacific and Indian or the total. The heat transport, this green line in the Atlantic, is northward everywhere. So it's northward in the southern hemisphere, it's northward in the northern hemisphere. In the Pacific Basin, you have heat transported from tropics to high latitudes, so equator to poles, evenly in both hemispheres. The Indian's interesting in that you mostly, well, there's no Indian Ocean up in the northern hemisphere, so you only get that southern half of it. But in the Atlantic Basin, you have heat being transported from the southern hemisphere to the northern hemisphere. So it's really important in understanding the asymmetry between climate in the northern hemisphere and climate in the southern hemisphere. And this is done by the AMOC. The AMOC is the reason why you have northward transport everywhere. So one important reason why we care about this asymmetry in the heat transport is because we think that it's related to tropical rainfall. You can kind of explain why we have more rainfall in the tropics of the northern hemisphere than the southern hemisphere through the AMOC. And this was a study I was involved in when I was in grad school. So heat release by the ocean when you have sinking occurs in the winter. This warms the northern hemisphere relative to the southern hemisphere. This affects the storm systems in the atmosphere. So if it's warmer up here, if it's warm, let's get the arrow back. If it's warmer up here in the Atlantic, storm systems don't have to transport as much heat poleward. So they get a little weaker. And if the storm systems in the northern hemisphere get a little weaker, then the Hadley circulation in the tropics, which is responsible for the heat transport. So the Hadley circulation has upward motion in the deep tropics, and then it has motion going in its upper levels, going poleward, sinks back down in the subtropics, and then converges moisture at the surface into the deep tropics again. If the storms become weaker in the northern hemisphere relative to the southern hemisphere, the Hadley circulation also doesn't have to transport as much heat poleward. If it doesn't have to transport as much heat poleward, this northern hemisphere cell of the Hadley circulation becomes just a little bit weaker, and it doesn't converge as much moisture into the deep tropics, into the rain belt. And so as a result, the other cell becomes stronger. This occurs on a seasonal basis. In the summer, the Hadley circulation moves into the northern hemisphere where it has this sinking, and then it moves back south when it's southern hemisphere summer. But by having the ocean release extra heat, affect the storms, affect the Hadley circulation, it gives the whole Hadley circulation just a bit more of a bias to the northern hemisphere, and that results in getting more rainfall into the northern hemisphere as well. And so this is an interesting way of saying why the AMOC is important for climate, because it influences rainfall in the tropics where it is. This is kind of where I started out in grad school, was thinking about tropical precipitation. And it really interested me that it's the ocean that's important for helping set where this is happening. So that's kind of context for where I started and how I've gotten to where I am. Another reason we care about the AMOC is because it influences variability in the Atlantic Basin. So in particular, something called Atlantic Multidecadal Variability. Multidecadal meaning that it has this kind of characteristic period of maybe it's in a low phase for a decade or two, and then a high phase for a decade or two or three, and then it goes back and forth. This is also called the Atlantic Multidecadal Oscillation. It's not a true oscillation. So a true oscillation between the ocean and the atmosphere would be like the El Nino Southern Oscillation. And so in the Pacific Basin, where you can use equations that are related to waves, so an oscillation, to explain its behavior. But this, the Atlantic Multidecadal variability, you cannot explain it using wave dynamics. It's not a true oscillation. So there's been a push in the community recently, especially, to get away from this term of Atlantic Multidecadal Oscillation and instead call it something a bit more true to what it is, Atlantic Multidecadal Variability. So I'm trying to get out of that habit as well and call it AMV rather than AMO. That's also convenient because AMO and AMOC are only one letter different. So if you call it AMV, it's a lot easier to not be confused about what the heck you're talking about. So in a lot of different climate models, and most every climate model that I read a study for, we see that the AMOC influences Atlantic multidecadal variability. So when you have a stronger AMOC, you also have extra warming in the northern hemisphere. This makes sense because when you have a stronger AMOC, you're having more heat release from the ocean to the atmosphere, and that the atmosphere can respond to that. Something interesting, however, though, is that there have been no I'm quoting someone else here on this because I'm not an observationalist. There have been no convincing observational studies that have proven that the observed Atlantic multidecadal oscillation, Atlantic multidecadal overturning circulation influences Atlantic multidecadal variability. Our time series are very short. We've only, our observations don't go back far enough to really say, well, do we have a whole, enough of these oscillations, periods, to say one way or the other clearly yet if the AMOC influences AMV in the real world. In models, it sure does. So that seems like, and that gives us enough reasoning that we should be studying this connection in models until our time series become long enough that we can say one way or the other clearly, does the AMOC affect AMV? But there's and so this is important. So AMOC influences AMV. And the Atlantic multidecadal variability has a number of proven climate impacts. When you have a high period of Atlantic multidecadal variability, you have more Atlantic hurricane activity. It affects the amount of Sahel precipitation. So the Sahel is south of Sahara in Africa. It's a key region for agriculture there. And when you have modulations in what the Atlantic multidecadal variability is, which is just a way of saying how high the SSTs are in the Atlantic, that affects drought in this region. And so that's kind of interesting that you can connect precipitation in the Sahel to the overturning circulation in the Atlantic through this variability mode in the atmosphere. There's also research that shows that US rainfall and droughts are also influenced by Atlantic multidecadal variability. Arctic sea ice, likely through more ocean-related processes in the North Atlantic. And then summer temperatures in Europe and North America are also related to Atlantic multidecadal variability. So understanding this variability, what influences, what causes it, has a number of important climate impacts that could help us with perhaps coming up with better climate predictions. Something interesting in the field right now is that there's been a push towards decadal climate predictability. So weather models, what we can say, weather models will only give you a good weather forecast out to 7 to 10 days because after that point, you have a lot of chaos in the system. So that what you may have heard of as the butterfly effect. So you can only go out about 7 to 10 days before before all of the different realizations, all the different storm systems have diverged from what is actually going to happen. So that's one prediction where you can only go out so far. But with climate predictions, you're not banking on getting the exact temperature and winds over one place. You're just trying to figure out, is there a greater probability of there being more precipitation in the Sahel or higher temperatures? You don't want to know on January 3rd of 2020, what's the temperature going to be? You just want to kind of know, will it be warmer than average? And in the field right now, there have been some decadal climate predictability systems in research right now, which are showing, yes, we can figure out what the probability of it being higher or rainier to a certain extent from what it normally would be with some skill, which I think is super exciting. So that's another reason for why we should, and a lot of that skill likely comes from the slow ocean circulation. If the ocean takes much longer than the atmosphere before it diverges from where it should be in a model, that you can use that slow amount of time to learn something about what the other climate impacts are elsewhere. So because the ocean takes time to diverge from where it might actually should be going, you can use that for a couple of years to make skillful predictions. Or so we hope, and so it seems like in a lot of the recent literature. Which is something I'm super excited about, at least, because that's really cool, right? That you can make predictions out 5 to 10 years about if there's going to be rain or drought, especially in like someplace like the Sahel, with some skill. So look for that in the next 10 to 20 years as our systems get better in that sense. That's a really exciting area. So I've talked a little bit about weather systems, and then there's those decadal climate predictability systems. The systems for the decadal climate predictability are the same models that we use for climate projections. So right here I have an intermodel comparison of a bunch of different climate models, and they force them with greenhouse gases. And this is so that they all have different models. The different models all have different physics in it, which is why you have this huge spread, but they're all forced with the same greenhouse gas emissions. In this case, these emissions are sometimes what you may hear called a business as usual case or high emission scenario. So if we keep emitting carbon dioxide and methane at the rate that we are now, this is the kind of what you would expect to see. And so it looks like a bit of a cloud because all of these models have a different mean state that they're starting from, but all of them decrease. So this is from a 2005 model intercomparison project where they looked at the AMOC strength in a bunch of different models, and they decrease. And since 2005, this result that you will see a weakening of the AMOC in the future due to greenhouse gases is an older result in 2005, and all recent results since then have also shown the same thing. So at least there's a lot of different literature out there about what drives the AMOC, and I'm not going to get into that today, but I think mostly in the North Atlantic's perspective. So from the North Atlantic, where you have the sinking, you have to think about, so what's going to change with the AMOC because of global warming, that's going to change what's going on in the North Atlantic, which is where the sinking occurs. So for water to sink in the North Atlantic, that water needs to become more dense than the water below it. So how can it do that? Well, it can invect in denser water, either water that is saltier or water that is colder. So you imagine that the Gulf Stream is what transports the Gulf Stream and the North Atlantic current. They bring salty, warm water from the subtropics into the high latitudes. So clearly with global warming, we're not going to be invecting colder water, but maybe we'll be invecting saltier water. But if the AMOC, here's another interesting, if the AMOC slows down, then this ocean transport will also slow down. And water also, to become denser, you can also make it denser by losing fresh water, so by evaporation. So you evaporate the fresh water, leaving the salt behind. This makes it denser, and this is what occurs. This occurs in the season. You could imagine you have changes in runoff from rivers. This would also affect the amount of fresh water relative to salt. This is in the winter time. This occurs every year, which is why you get sinking. You lose heat, and it's the latent and the I lost a word in there. Latent and sensible heat fluxes, what are called the turbulent fluxes, are what take heat away from the ocean surface into the atmosphere. And so it loses its heat. It becomes denser. Once it's denser than the water below it, it can sink. And this occurs seasonally every year. So by losing heat, you can make the water denser. So changes to advection of the AMOC, changes to how much fresh water gets evaporated, how much heat, that can all affect the ability of water to sink in the North Atlantic. And if you decrease the amount of sinking in that part of the overturning circulation, you could imagine that the rest of the overturning circulation would somehow have to slow by conservation of mass. So what I'm going to talk about for the rest of this talk is some of the recent research that I've been doing on climate variability and climate change. And I use a tool called the Community Earth System Model, CESM Large Ensemble. So I'm in Boulder, Colorado, and we have one of the world's premier climate centers in town. And one of the models they make is the Community Earth System Model, CESM. About a couple of years ago, they decided that they were going to do what's called a large ensemble. So an ensemble meaning you run the model a bunch of different times, but you start off the initial conditions very, very, very slightly differently so that they look almost identical, but it allows the solutions in each model to diverge pretty substantially. And when I say very, very small changes, I mean it. So the way they initialized, so they spun up the coupled model for, I think it was 2,000 years-ish. Then they started it with 1850 pre-industrial, so before we started emitting really high greenhouse gases. They run it, and then in 1920, they start 40 different members of this ensemble, 40 different climate runs. And the only thing they do to distinguish these different runs is they perturb the temperature in the atmosphere at every point by 1 × 10 to the negative 14 Kelvin. So this is round off error in the computer at the very end of the float or double in computational land. So very, very small. So way below what our observations can tell, very, very tiny. And yet this allows each member to end up in a slightly different place. So these gray lines here are all 40 members lying on top of each other, and the black line is the mean of all 40 members. So from 1920 to 2005, they use historical forcing. So historical forcing meaning historical greenhouse gases, carbon dioxide, methane, historical ozone, historical aerosols, historical volcanoes, everything that we've known it. After about 2005, they use what's called representative concentration pathway 8.5 forcing, which is a high emission scenario, a business as usual scenario. So what you can see when you take the average of all of the different members, you can have a very clear idea of what the response to the forcing is. You are averaging out all of the internal variability. So you're averaging out the low points and the high points, and you get a sense of, okay, this is what greenhouse gases and ozone and volcanoes all together are doing. This plot here is the AMOC strength in this CESM Large Ensemble. And what you can see is that there's some modulation of the AMOC strength, very, very slight, like plus or minus 1, what's called a sphere drop, which is 10 to the 6 meters cubed per second. So very, very small modulation. But once you turn on and you start seeing a downturn at the end of the 20th century and recently, but you can't really tell yet if that forced response, so how much the greenhouse gases are forcing, is outside the more natural variability, what we think is probably natural variability, or the natural forcings that were in the atmosphere in the 20th century. But after that point, it starts decreasing substantially. So this is the strength of the overturning circulation as we estimate by the model in 2100. It's about 40% lower than it was in what we think the model is today. This model is one of the best climate models in the world. I might be a little biased because I'm in Boulder, but if you look at a bunch of different model intercomparisons, this one definitely has more skillful representation of numbers of different phenomena in the atmosphere. So this is a strong model to use for these kind of processes. Its representation of the AMOC is a little stronger than observed, but not too far out of the envelope of where it should be, especially in comparison to some of these models. Some like this one here is way too low. This one's here way too high. This is in the right ballpark, maybe off by about 2-3 sphere drops of mean strength as I am measuring the mean strength. So here's the same figure we just showed. So the AMOC strength in all of the large ensemble members, and then the ensemble mean, so the part that's due to greenhouse and ozone and all of the different forcings. This is what the overturning circulation in the Atlantic looks like. So here's about 30 south, here's the North Pole. You can see, so this is the overturning stream function. And so you can imagine if you just follow these lines of streamlines, that shows you which way the circulation is going. So near the surface, you have poleward transport, you have downward motion up in the high latitudes, and then you have return motion at 2,000-ish meters back. And so this is what the pre-industrial AMOC looks like in this climate model. This is this portion of the run. And then this is the change of the end of the run, 2080, 2100 average, minus this pre-industrial point. So you measure the one way of measuring the strength of the AMOC is to take the maximum overturning stream function number. So the darkest color in this case. So that looks like about 28. And then you lose about 12 sphere drips in the model, which is about a 40% decrease in strength. So you can see that the blue is in the opposite direction. So this is a change in this direction from the mean, which was going this way. So it hasn't reversed. This is just the change from here as projected by the model for the around the 21st century. So why does it slow down? This is my recent work showing it's not terribly different from what's been done before, but I get to control the figures, and show exactly why. So we see that the AMOC slows down, especially as measured in a North Atlantic metric around 40 north. Why does it slow down? If we're looking in North Atlantic where things are sinking, then we should be thinking about what is the surface density? What's the surface density looking like? On the left here, I have pre-industrial surface density in the North Atlantic in the CESM model. So the shading, the color, that is the density of the surface. So reds are the densest, blues are lighter. The black lines are what's called density flux, where the density flux is positive. So the solid contours, that's indicating a region where you are losing heat or fresh water, and that allows water to become denser. The white contours are the mixed layer depth. So how far down is the ocean sinking at that place? So you'll see that there's maxima here in the Labrador Sea. You also have a positive density flux, meaning that, yes, the atmosphere above and all of the other fluxes are in such a direction that you are losing heat, so things can sink. And you have relatively high density. And the mixed layer depths being deeper there indicate that this is where you're having sinking. You also notice a few little places along the Greenland and Iceland area where you also have maxima. But this Labrador Sea is one of the ones that is larger. So this is the change by 2080 to 2100 of the surface density and this density flux. And the density flux is just heating and fresh water, and whether the heating and fresh water allows water to sink or not. You'll notice that the density decreases everywhere, that the water is becoming lighter at the surface everywhere, and it's not changing below. So this is increasing the stratification of the ocean. It's becoming lighter water on top, and so it makes it harder to get water to sink if it's lighter on top. You need to have a lot more forcing to get that water to sink. And you'll also notice that these dashed lines indicate negative density flux. So this is the change in the density flux. And you are decreasing how easy it is to get this water to sink. So not only have you made it lighter, you're not forcing it to sink as much. It makes it harder for that water to transform. So the blue and the black contours here are changes, but I also just plotted the 2080 to 2100 mixed layer depth, just the same quantity as this white lines on the left. And what you'll see is that there's no more sinking down below 400 meters in the Labrador Sea in 2080 to 2100. It's so much lighter and there's so much low forcing that the sinking is not occurring as regularly, and there's not as much sinking. So from a North Atlantic perspective, when you're thinking about the sinking, this is why the AMOC is slowing down. And so, okay, what is the density? What is changing the density? So if we just take a look at really quickly the two things that affect it most, the change in the surface temperature, change in salinity, you'll see that both in much of the North Atlantic, when you have temperatures increasing, that makes density lighter. So you have in the Nordic seas especially, this temperature increase is causing this density decrease. But in the Labrador Sea, you can see this pattern of salinity change really nicely matches the density change. So the water is becoming fresher in the Labrador Sea in the North Atlantic, and that's causing the water to get lighter. What's causing the water to get fresher, I haven't looked exactly into those reasons, but it's probably, there's a couple of reasons why this should be getting lighter. One is that under global warming, one of the very robust results we see is that the hydrologic cycle increases under global warming. So that means where you have evaporation, especially over the ocean, you're going to get more evaporation. And where you have precipitation in the mean, you're going to get more precipitation, even more. And in the storm track region of the North Atlantic, this is a place where you have precipitation in the mean. So all the time, more precipitation than evaporation. And under global warming, you expect there to be even more precipitation. Precipitation adds fresh water to the surface, making it lighter. There could also be some impacts due to melting sea ice. That'll also freshen things up. We also, related to that change in the hydrologic cycle, you'll affect how much runoff comes from rivers. And there's a lot of rivers that drain off Canada and the St. Lawrence Seaway into this region. That'll also affect the amount of salinity. And then this model does not include melting from Greenland, but Greenland melt will also increase the amount of fresh water that's in the North Atlantic. So all of these processes are going to decrease the salinity and decrease the density. And there's been a lot of research out there. If you want to learn more, I'd be more than happy to point you in the right direction. So we've been talking about this forced response of the overturning circulation to greenhouse emission, and that's that it's weaker. So I have these 4 different parts of the large ensemble. One is just this pre-industrial area where you're looking over 100-year trends. You can see on average, or in the pre-industrial, you average all the different trends, you get to 0. This red blob is a historical part of the ensemble. So each of the light colors is one member, one run. Then you average them all together to get what the forced response is. And you can see that compared to pre-industrial, that forced response has a weakening of the AMOC strength and an increase with global warming. You can use 2 different forcing scenarios. So we have this RCP 4.5, which is a medium emission scenario. So not as much as we're emitting now, not on that path, but still not little. Or the RCP 8.5, which is what I've been showing results from so far. And you see the more forcing you add, the more the AMOC weakens and the more global warming there is. And as I just explained, it's the global warming that's forcing the AMOC decline in this case. Global warming is increasing precipitation, increasing runoff, all of that, which decreases salinity, which weakens the AMOC through making it harder to convect and form deep water. But something interesting you can see is once you take out this forced response, if you look at it, there's a trend in the opposite direction when you look member to member to member, just relative to that forced response. And what this says is that for a model whose AMOC weakens less, there's slightly more global warming. So this is the internal variability portion that is inherent in the system. And this is why this CESM Large Ensemble is so powerful, because you can separate forced from internal variability. And if you divide up, so we take out the forced response and just look at, in the I'm going to show the historical response, where is this warming occurring? So when the AMOC is stronger, where is warmer? You can see that there's more warming globally when you have a stronger AMOC. So this is the pattern of wind and warming that you can attribute to the AMOC strength. So what this shows is that when you have an AMOC that is stronger, where is there more warming? You see there's more warming over Europe, and there's more warming over the North Atlantic and warming over the Nordic and Barents Sea near the sea ice edge. So this is the trend that would be on top of this forced response. So you can see that this amount of warming is relatively small in comparison to the forced response. You only get maybe another 0.1, 0.2 Kelvin in comparison to the forced response. So relative to the forced response, this variability is small, but it is important regionally. You can see that you can have up to a degree or 2 of extra warming near the sea ice edge that you can attribute to AMOC strength. And so this is also the wind pattern that is associated with stronger AMOC. And something interesting is that you have stronger winds over the Labrador Sea. And the Labrador Sea is a key region, again, for sinking. Winds can help drive those turbulent heat fluxes. So when you have evaporation from the surface or you have heating from the surface of the ocean upward, winds help influence that. This is what influences the AMOC strength. So by having these winds strengthen, at the same time you have a strengthening the AMOC, that means that the winds could be what's driving the variability in overturning circulation, and then the overturning circulation transports heat poleward, which warms up Europe and Eurasia. However, there's a second possibility here. What if you don't need ocean heat transport? What if just these winds are blowing, come back arrow, these winds are blowing heat across the ocean and just transporting heat itself from one place to the other. The question then becomes, do you need an ocean circulation to get this warming patterns associated with the AMOC, or is this ocean variability going along at the same time, and just coincidentally you have a stronger AMOC at the same time you have more warming? So one way to try to assess this is to compare 2 simulations in the CESM Large Ensemble framework. One is a 2,000-year-long simulation with the full dynamic ocean, everything in it. And the second one has a simpler ocean model. It's just completely static, there's no motion, and it only allows the ocean to take in heat and release heat, but it doesn't move. So you've gotten rid of the ocean heat transport part. So what this says is, okay, we have simulation on the left, which has a mixed layer ocean, very simple, and then the full simulation. And then we said, okay, well, the Labrador Sea winds in that region seem to be related to whatever's driving this variability. So let's figure out what the temperature pattern in both of these models is that goes along with this pattern in warming. And so if we just take the average wind in this area and relate it to what the warming pattern looks like everywhere, we see that we get, in both simulations, we get warming over Europe, regardless of whether you have a dynamic ocean. Interestingly, it's over the sea ice edge where you get all of the extra warming that's related to this wind pattern here that only occurs when you have a full ocean. So what this says is that the sea ice response up here and the temperature pattern requires the presence of a dynamic ocean to occur. But this warming over Europe, you can't say either way whether you need the AMOC to be transporting that heat or not. Because these two simulations look the same, you cannot tell them apart. And there's such different dynamics in these two simulations that you cannot say what is the role of the ocean in warming Europe. You can only say that they look the same, so you cannot say. But up at the sea ice edge in the Nordic and Barents Seas, you can say that AMOC transports this heat and is necessary to give you that temperature response. And this agrees really nicely with previous research that's been done that says, well, how is the AMOC important for influencing surface temperature? And the idea out there is that if here's our overturning circulation in the ocean again, the overturning circulation transports heat poleward from the warm tropics to the high latitudes. And this affects climate feedbacks. So this climate feedbacks being sea ice and clouds. And something that's interesting about the climate system is that climate feedbacks are not the same value everywhere. Climate feedbacks are more positive in the high latitudes than they are in the low latitudes. So if you're taking 1 unit of heat from the tropics and taking it to the Arctic, that 1 unit of heat will then give you a bigger response in the temperature in the high latitudes, so up here in the Arctic, than it would have if you just left it in the tropics. So you can get more warming overall by transporting heat poleward. And this agrees really nicely with the figure I showed previously. You see the warming that is associated with the AMOC strength is along the sea ice edge. So it is the sea ice feedback that is adding to the amount of warming you get in response to a variability in ocean circulation. So that agrees very nicely with previous research. So to wrap up, the AMOC is an important component of the climate system due to its transport of heat. It's also important for transport of carbon and freshwater. I focus most on heat because I tend to take a thermodynamic view of how the climate system works. The AMOC likely influences Atlantic multidecadal variability, which has a number of climate impacts ranging from Sahel precipitation, Atlantic hurricane activity, and drought and temperatures in North America and Europe. Under a high greenhouse gas emission scenario, the overturning circulation in the Atlantic is projected to weaken substantially due to global warming. This will likely have impacts on these on different impacts around the Atlantic basin and globally because you've changed how much heat is transported and throughout the entire climate system. Variability in AMOC strength influences the amount of warming you have in the Northern Hemisphere. It is a smaller response than we expect to see due to the forcing, but it still is notable in certain areas of the North Atlantic, specifically in the Nordic and Barents Sea near the sea ice edge and over northern Eurasia. For further reading on the AMOC and its influence in climate and weather, I've provided a few links. Melissa has these and she can post them on the website if you don't want to write these down right now. Here's the first are a couple of one's a video of a professor who is somebody I highly respect, Susan Lozier, on observing the AMOC. And she works at Duke, and so the video is actually promotional Duke material, but the presentation is really good. So just get past the 1 or 2 minutes of, oh my gosh, Duke did this for me, blah, 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 and get to the part where she talks about observing the ocean. And then this is a nice nature news and views where they talk about how we are observing the AMOC. That's something I didn't talk much about today because I'm primarily a modeler, not an observationalist. But we've, in the last 10, 15 years, our observations of the AMOC have increased a ton due to different and new observational platforms that we've got out there. Something I didn't talk about much is this idea of, there's this popular idea that the Gulf Stream is important for keeping Europe warm in the winter. That idea is getting more and more pushback these days that it may not be that relevant. So here's a nice article about is the Gulf Stream and the AMOC important for European winter. Here's a bit more of summary on Atlantic multidecadal variability from some other scientists here in Boulder. There's this really nice climate data guide that's put out by the National Center for Atmospheric Research. They have a bunch of summaries on a lot of different climate processes and model and observations. So it's a nice resource if that's interesting. And then this last one is a very thorough experts review on the AMOC for any of those who are interested. If you're interested in any part of the overturning circulation in the Atlantic, this paper is written by Martha Buckley. And it's very, very thorough. You will find your answer in there. She also takes a very thorough and even-handed assessment of every part of the literature. She doesn't have any biases that seem to seep into her review. So if there's something very, very specific you want to know about the circulation, it will be in that review, probably. So I'm happy to take some questions now. I'll turn it back to you, Melissa.
Okay, yeah, so this is the section where it's really beneficial for you to be a live participant in the webinar because you get to ask all your questions. So definitely, if you have a question about anything in the presentation, make sure you type it into the chat box. What I'll do is I'll read it aloud just so that we can keep everyone muted again to keep background noise to a minimum. So give you a minute or two. Like I said, definitely ask questions because you've got the expert here to be able to answer.
I'll turn back to the summary slide. That might help too.
I feel like this is sometimes like asking students a question. Nobody wants to be the first, but once somebody asks a question, there's usually more that come in.
Yeah, when I was a TA, what they told us in that situation is you're supposed to sit there and just stare them down, and eventually someone will say something.
Lucky for them, I can't stare them down through a webinar. But I'm sure there's got to be at least one question out there.
I also work a lot on tropical precipitation if anyone wants to ask me about that, the intertropical convergence zone, which is more atmospheric than ocean, but I'm happy to talk about it. Okay,
one question came in. They said, do you think that the decline in the AMOC will affect weather in inland U.S. regions like Colorado?
My guess would be, well, okay, I've got two kind of answers to that. So most of the climate impacts that we see associated with AMOC are through Atlantic multidecadal variability, and most of those impacts are very closely related to the Atlantic. So in that sense, the changes in U.S. drought and rainfall that you can associate with this mode of variability are more on the Atlantic side than Colorado, so not. However, because the AMOC is such an important part of the heat transport in the entire system, you will be affected because if you're thinking of this purely in how you're transporting heat and how that affects the thermodynamics of storms and everything in there, then by decreasing the heat transport that is done by the AMOC, you will certainly affect what's called the baroclinicity. So baroclinicity is how you are able to generate storms. And you'll affect that throughout the Northern Hemisphere because atmospheric circulation makes temperature anomalies really, really fast relatively. So in that sense, decreasing ocean heat transport will affect the atmosphere. And there's a lot of research out there trying to figure out, well, how does atmosphere and its heat transport change in response to an ocean heat transport? It's like if you decrease the AMOC's heat transport by, say, a petawatt, will the atmosphere then increase by a petawatt? And there's evidence out there that maybe, maybe not. So it's kind of hard to say if the whole Northern Hemisphere will change the storm systems which do this atmospheric heat transport or not. But certainly it will be affected. But how that will exactly manifest into weather in Colorado is probably very difficult to say.
Okay. Any other questions? So the question is, so AMOC has some influence on Arctic ice. However, what kinds of impacts would a decreased AMOC have on Arctic ice? And how specifically do you know what the effects would be?
Oh, that's a fun question, because that gets into another coupled feedback. So a decreased AMOC, you would imagine if the primary way the AMOC affects sea ice is through heating. So when you have a decreased AMOC, you're not transporting as much heat into the high latitudes. You would therefore get an expansion of the sea ice relative to where it was. You get more sea ice. Here's where things get interesting. There's research out there that shows that sea ice, also influences the AMOC. So sea ice, when it melts, it makes things fresher, which would weaken the AMOC. And sea ice, during the seasonally, when you refreeze sea ice, it rejects salt. Only the fresh part of the water freezes. And so that makes water saltier. It's called brine rejection. And that could possibly influence the AMOC. So it's a coupled feedback here. The AMOC transports heat, which influences sea ice. But sea ice, when it expands, could also influence the AMOC. So another way sea ice influences the AMOC is sea ice insulates the ocean. So you have a layer of sea ice over the surface. You can't exchange heat from the ocean to the atmosphere. The sea ice is in the way. So it really effectively caps off the ocean, and if it doesn't lose that heat, it can't sink. So there's all these different effects that sea ice can therefore play on the ocean circulation, keep it from sinking, and feed back on the system. And that's another area of research I think is really interesting, and I've got a couple of ideas for future projects with that. There was a cool study by a professor at Yale, Alexei Fedorov, in the last year, where they look at this exact question of, does sea ice drive ocean variability in the Atlantic or not? But we know for sure, the Atlantic overturning circulation affects sea ice. How much does it go the other way?
Okay, so the same person said, interesting. So is it difficult to know for sure what can happen, especially when climate change is thrown in?
To some extent, yes, it's difficult to know exactly what's going to happen, but we know most of what's going to happen, especially at large scales, fairly well. With response to the ocean, with respect to the ocean, we know the AMOC is probably going to decrease substantially. We know that sea ice is already melting back. We know that sea ices can continue to melt back. We know the Greenland ice sheet's going to melt back. And so on these large scales, we're fairly certain about what's going to happen. Where we're uncertain is at very small regional places, especially at shorter timescales. So by shorter timescales, I'm saying like out to 2050. There's still a lot of internal variability in the system that hasn't yet gotten smaller than what the forced signal is. So there's a concept out there called time of emergence. So about to 2050, sometimes the time of emergence for the warming signal may or may not have occurred yet, but it depends what you're looking at. For instance, with sea ice, we've already seen sea ice declines, and with Greenland ice sheet melting, you've already seen the Greenland ice sheet starting to accelerate with its melting. So it's hard to know exactly what's going to happen, but we know the sign, we know which way it's going to go. We don't know the exact amounts, but we know pretty well what it's going to be. So by 2100, the world will be a very different place than it is today in the natural world because of global warming. And something that's interesting about, so I'm just really getting started with my career since I've only recently finished my doctorate. And it's going to be very interesting to see what the world I'm studying is going to be like towards the end of my career. Assuming I'm able to stay in this field for a good 30, 40 years, that'll put me at maybe 2050. And it'll be very interesting to see how these predictions have come true. How much were we underestimating? Were we overestimating? In what parts? It's an interesting time to be a scientist. It's also unfortunate because I'm going to have kids sometime in the next couple of years, right? And I want to share these things, these places that I've enjoyed seeing my entire life and traveling to with my kids, but they're going to change so much. And it's an interesting time to be a climate scientist.
I'm sure for more reasons than just that too.
Oh, yeah.
Okay. Yeah. Any other questions? Are there any similar systems to the Atlantic multidecadal variability in other oceans?
Yes, there are. In the Pacific, there's what's called the Pacific Decadal Oscillation. It's not really, again, it's not really an oscillation. It's just sort of this mode of variability. And when I say oscillation versus variability, variability meaning that you cannot say it's a wave-like thing where you have a wave driving it. Pacific Decadal Oscillation has about a decadal period. It has a lot of effects on climate, especially in like the northwest of the US and Canada. For instance, you can see the response of the PDO, Pacific Decadal Oscillation, in the salmon returns in Alaska and in British Columbia. So I forget which exactly way it goes, but when the PDO is high or low, it affects the temperature in the ocean, which affects how salmon are able to go back and spawn or not, or how much salmon you're able to catch. So that's kind of a cool one. There's also the Indian Ocean dipole. I'm not as up on the literature on that, but that's another mode of variability that's especially important. The Indian Ocean, I think it's got relations to the monsoon. So those are like the similar-ish timescales to Atlantic multidecadal variability, so modes of variability on 10 to 20-year periods. And then there's also there's also the most famous one that's actually an oscillation, the El Nino Southern Oscillation. And that has huge climate impacts globally. And that's when you have, that has to do with how the warm pool in the Pacific sloshes back and forth with the cold tongue, and how the atmosphere and the ocean couple, and how that affects the thermocline, and that couples into everything. On even shorter time scales, there's what's called the Madden-Julian Oscillation, which is primarily an atmospheric phenomena, where you have extra rainfall that propagates across the Indian Ocean and the Pacific every 30 to 90 days, especially this time of year. And that one's important for, it sort of like tickles the jet, the Pacific jet as it comes through. So there's some climate impacts in the US that can come from the Madden-Julian Oscillation, the MJO. Those are ones that come to mind. If you go to the literature, there's a whole alphabet soup of things that people have named. That they found, oh, here's a European blah 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 blah. But those are the big ones that are usually you can see some power in when you're trying to figure out what climate impacts are important.
Okay, we have a few more minutes if anyone else has a question. Okay, if not, I'm going to quickly show you. I'm going to share my screen now so I can show everyone. See if it'll let me.
Should I stop sharing my screen?
No, this should be okay. Since I'm the presenter, I think it'll work. Okay, just wanted to let everyone know. Let's see. Okay, hopefully everyone can see the NOSB website now. So I just wanted to let you know, if you go to the National Ocean Science Bowl, so it's nosb.org, you go to Learn, and then Professional Development Webinars. This is where we're keeping all the links, either to the upcoming webinars and afterwards the links to the recordings. And here, if you click on Dr. Maroon's page, at the bottom you can see there are the links to those resources that she mentioned during her presentation. So that's where you can find everything. And if you were following us on social media, we'll post the links to the recorded video tomorrow on there as well, so you can share them. This webinar series, obviously, we posted on YouTube so that everyone can use it to their benefit. So definitely share with other teachers, with your teams, anyone you think might be interested in it. Once it's up on our YouTube page, it'll stay up there. So with that, I don't see any other questions coming in. So I'd like to thank Dr. Maroon for presenting today. This is definitely a different topic than we've had presentations on in the past, so I hope everyone enjoyed it. As I said, the recordings will be up shortly, and definitely be sure to share these links that she provided. You can also come back to this page. We're working on getting a handful more of these webinars set for December, so definitely come back to this webinar site to check on when those will be. We'll also, if you're on our listserv, we'll also send an email with the links to the upcoming webinars. Okay, so if there aren't any other questions, we'll end for today. And I'd like to thank Dr. Maroon again for presenting. It was a great way to kick off our year discussing how our oceans shape our weather.
Happy to help. Thanks.
Thank you. Have a good afternoon, everyone.